Hi, I'm going to be talking about chemicals in context, and specifically about chemically enabled text mining. So how Linguamatics natural language processing can be used with chemical intelligence from ChemAxon. My name's Jane Reed, and I'm going to be co-presenting with Dr. Andrew Hinton. So when we think about the challenge, it's really this: how can you capture the whole picture of chemistry with the biology around it? And really, how can you connect chemicals, however described, to the biological context? I think we're all getting familiar with the tools that can extract chemical names and structures from literature. But being able to associate meaningful and actionable biological context to that extracted chemistry remains a challenge. So Linguamatics Agile text mining software, I2E, can quickly and scalably contextualize chemistry described in literature. You can use our NLP software to uncover assertions, facts, and relationships associated with chemicals found in patents, in scientific literature, in drug labels, and more. A little bit of background, Linguamatics natural language processing in essence transforms unstructured text into structured decision support. Our NLP frees the insight trapped in scientific and clinical text for decision support bench to bedside. Linguamatics was founded in 2004, and for 15 or more years, we've been delivering natural language processing solutions to healthcare and pharma clients. Our customer base includes 18 of the top 20 pharma, leading healthcare payers and providers, and government organizations such as NASA and the FDA. And our core value is we provide superior natural language processing, including ontologies, normalization for concepts, quantitative data, multilingual text mining, and context such as negation, and much more. It's a multi-mission capability that can be applied across the enterprise, and as well as the software, we also provide some content and services. So when we're talking about natural language processing, what in essence do we mean? We really mean that we can transform snippets of text like this to structure, so really moving from words to meaning. So here this snippet is, among them, nimesulide, a selective COX-2 inhibitor. The first thing our software can do is identify the entities and the relations. So here we know, the software knows that nimesulide is a compound, and it's been mapped here to a structure. That COX-2 is a particular protein, and it's been mapped here to an entry gene ID. And that we can use the linguistics to establish the relationship between these two concepts, from the word inhibitor to the relationship inhibits. And that can then be transformed into a semantically normalized triple. This particular structure inhibits a particular protein ID. And once you have that semantically normalized triple, that's hugely powerful. You can create hundreds or thousands of these triples from text, and then integrate them with knowledge bases, analytics tools, graphing tools, machine learning models, and more. So when we're thinking about that biology and the connection to chemicals in text, you want to be able to find both named compounds and novel compounds. On the left-hand side, think about named compounds. You can use a terminology ontology approach, and Linguamatics provides things like Chebi, NCI thesaurus, and these provide hierarchies of chemical concepts with synonyms and other identifiers. And they bring value to a huge variety of drug-related projects, but they cannot identify novel compounds. And for novel compounds, not listed in ontologies, you need to use something like ChemAxon's powerful name to structure, which can assign structures to novel chemicals mentioned in text. And obviously, if we can assign structures, you can then search text via substructure and similarity search. And Linguamatics have been partnering with ChemAxon for this chemical-enabled text mining for over a decade. So before I hand over to Andrew, I just have one use case to talk about. This was presented at one of our user group meetings by a group at Roche who've created an integrated chemistry workflow that they call Artemis to answer drug discovery research questions, specifically focused on the sort of questions that medicinal chemists need. So they need an efficient access to the landscape of information on compounds and the relationship of compounds with targets and diseases. And this information is often buried in unstructured text. So Roche have used Linguamatics natural language processing software, chemically enabled for text mining to extract relevant compound, target, and disease information. This is normalized using our NLP structured, and the integrated data is extracted and then presented in an analytics-friendly format in spot file. You can see here they're pulling information from a dozen different data sources, which range quite broadly. And this really empowers their drug project teams to easily ask questions about what's known about chemicals and associations to targets, safety or toxicity information. And critically here, you can see that search times have been cut from around 2 weeks to a few hours. So, our natural language processing solution offers rapid, systematic, comprehensive access to critical insights from unstructured text, and integrating the chemical search capabilities from ChemAxon enables users to identify chemical structures and understand their role within documents such as patents, scientific articles, and internal reports. There's more on our webpage, but I'll now hand over to Andrew Hinton for demonstration.
So I'll be providing a demonstration of how Linguamatics' new Web GUI interface makes use of ChemAxon's technology to facilitate effective chemical text mining. And in this case, we'll be starting off with a simple substructure search over a sample of Medline abstracts. And as we can see, the chemical search is more prominent in the interface, and this allows the I2E user to perform either a substructure or a similarity search on those ontologies, those chemical ontologies that are available. And we see that within the I2E Web GUI interface, we've got the Marvin JS chemical drawing package interface embedded within it. And this really allows for really nice, easy, simple way for the user to draw a substructure. And here I'm drawing basic steroid scaffold, which I'm then going to insert in I2E query and submit that query. And we see quite quickly results should be coming up on the screen of where we found instances of that particular substructure. That's and these are all result relating. We're getting documents out, and we're finding in the blue there where the mention of progesterone as text has been found. We're seeing that we're making use of another ChemAxon piece of technology, which is the chemical depiction rendering capability. And it's trivial enough within the I2E to effectively add on additional chemical information, such as the SMAR string, by effectively adding the node ID and rerunning the query. And when those results come up on the screen, to then output that information to, say, Excel. But fundamentally, the capability, as highlighted in blue here, is that when we're finding a mention of a chemical term within the body of the text of the document, and we can see that we're finding that in this case in the title of Medline abstract, we're actually using ChemAxon's name to structure and also structure to name capability, where we're taking a fragment of text, we're recognizing that that contains chemical name, and we're converting it into chemical structure, so we can get the depiction and also the SMAR strings out. And when we come to do a similarity search, it's much the same thing. So effectively, we can start off with chemical, and in fact, we can copy case. Why don't we copy the progesterone term, and use that then to load that in as a chemical. And after that, we can then decide at what level we want to do, say, a similarity search. So we can get a preview of those chemicals within our collection of documents that match that similarity threshold. And we're able to multi-pick those chemicals really quite easily just by so clicking on the shift button, and we can click on that and then insert selected items and submit that through, and we'll have 80% similarity. However, the real power of that capability comes when we think about the chemical context around a particular chemical. So in this case, I've got preloaded my substructure search, my steroid, and the I2E query that I'm showing you on the screen here has the capability of looking for mentions of any particular chemical that's matching our, in this case, our steroid substructure in relation to different contexts. That would be the context of how that chemical may treat a disease, how it may cause a side effects, how it may interact with a gene, what dosage, and the strength of binding. So one can run this query, and when you run this query, you get a nice rendering in the I2E charting tool, and we can see again we're getting the chemical depiction being used, but more importantly we're able then to see the context of which the chemical is mentioned. So it then becomes trivial to slice and dice the information to say that you're interested in understanding how a particular chemical is, say, treating psoriasis. You can use the searches to then walk through the different chemicals to see those that are actually having a treating statements. Again, equally, one's interested in, say, particular dosage of a chemical, and to understand what the variability in your document sets is. This particular I2E query is providing that chemical context where we can see that actually for a single individual given chemical extracted from the free text on the fly, we're able to normalize the different dosage forms. So it's possible to see that actually this particular steroid, prednisolone, is given at 15 milligrams daily, but equally could be given at 40 milligrams, 20, 10, or 5 in some instances. So there's a wide range of variability there that we're seeing in the data around any given use of one chemical. And finally, it's possible to actually, using this charting capability, where potentially we're seeing information such as where we've got misinformation. So in this case, testosterone causing bone loss. Well, actually, it's the deprivation of testosterone causing bone loss. So in this case, we may wish to think of that as a false negative, and so we can actually potentially remove that. So that's really all I wanted to have to say, and thank you for listening to this brief overview of the chemical technology employed within the new I2E Web GUI interface. Thank you very much.